All right, so here is the practice test that I've given you on Compass. Now, like I said, there are two topics that are assessed on this test. That there are two types of questions from two different areas. First is metals and second is ionic compounds. Now, we're going to ignore the questions that relate to ionic compounds. We're just going to look at the questions that relate to metals. Now, the first question obviously relates to metals, and it's looking at one of the properties of metals. So you need to know all of the typical properties of metals, that they are lustrous, that they are malleable typically, and they're ductile, dense, hard, all of those things. So that's actually in chapter 3.1 of your book. Chapter 3.2, I think, looks at the metallic bonding model and looks at how you can explain each of those properties. And for sure, there'll be some questions that we'll see here which relate to metallic bonding model. It connects the properties with the model, okay? Now, metals are lustrous because, and if they say because, they're now looking for the reason. And it probably refers to metallic bonding model in some way. But here we are. The cations are free to move. That's not true. The electrons reflect light. That sounds all right. The cations reflect light and the electrons are free to move. Okay. Now, just as an exercise, there are a couple of these statements that are absolutely wrong. Cations are not free to move in the metallic bonding model. They're fixed, relatively fixed in place. The electrons are free to move. That's true. And some people might select this as their answer because it's true. Now, in the metallic bonding model, electrons are delocalized, so they have no fixed location, which means that they're free to move. But this doesn't actually explain the property of luster, that is shininess. So shininess is like when light can reflect off of the material. So it's one of these two that explains it. Now, cations don't reflect light, but electrons, because of their size, they're around roughly the same wavelength as light, so they're able to reflect it. And this is the reason why electrons reflect light here. So cations reflect light is not a true statement. Cations are free to move, not a true statement. But here are the true statements. One of them is applicable. Okay, the second question refers to ionic substances. We won't look at that. In the third question, we have a question relating to the extraction of iron from its ore. So this is from chapter 3.4. Now, you need to know how iron is extracted. You need to know all the reactions that are involved in the process and the main piece of equipment that is used in the extraction of iron ore, namely the blast furnace. Okay, so now the role of calcium carbonate. Now, calcium carbonate, which comes from limestone. Limestone is the raw material. Calcium carbonate is added to remove impurities. Now, the impurities that are removed, that need to be removed, include silicon oxides, aluminium oxides, and I think manganese oxides. Now, all of these can be removed with calcium carbonate. So calcium carbonate, its reaction, under high temperatures, it decomposes, so it breaks down into calcium oxide and carbon dioxide. Now, calcium oxide is very reactive towards each of these things here. And because it can react with each of those three things there, it removes them. Like it can remove those impurities. And it forms what we call slag. Okay, so let's look at the answers here. To remove iron oxide from iron, this is the desirable reaction that we want at the end of the day. So reduce the iron oxide to iron. This is the desired reaction, but this is not what calcium carbonate does. So it's not this one. Coke to carbon monoxide is another reaction. It's not what nothing to do with calcium carbonate. Remove carbon monoxide. We need carbon monoxide to react with the iron oxide to form iron. And then the last one, to react with silicon oxide, which is this one, to form slag. This is the single correct response to do with calcium carbonate. The next question, again, the production of iron. So chapter 3.4 also. What are the raw materials? So there are a few raw materials. First, we have the iron ore, which is made up mostly of hematite, which is iron oxide. That's one. Limestone is another one. We were just looking at it in the last reaction. We also have coke, which is like supercharged carbon. I feel like I'm missing one. Yeah, there's one more. We use air as well. So air, which is, and the component in air which we need is oxygen. So coke is in there. Iron oxide, which is in iron ore, is also one of the raw materials. And calcium carbonate, which is limestone, is one of the raw materials. But carbon dioxide is not. Carbon dioxide is something that we need to produce, and it's produced by the combustion of coke. So just to clarify that, coke reacts with the oxygen to make carbon dioxide. And this is useful for us because it further reacts with coke to make carbon monoxide. Okay, so these are the raw materials here, just to be clear. So I guess one thing to be aware of with this question is to read. I saw that they were asking for something that was not a raw material. Now, if you were going really quickly through this question, you might have read, which of the following is a raw material? And then you might have seen coke, and straight away you're like, oh, that's a raw material. Definitely. So you'll circle that one because you're familiar with it. And this question is a bit tricky because it represents iron oxide and calcium carbonate, not in the raw material forms, because limestone and iron ore is usually how we refer to those materials. So the next question asks about the process of quenching. Now, quenching is one of the forms of heat treatment. That is, it's a way of modifying metals. Now, you need to know the 3 different ways that metals can be modified through heat treatment. Now, quenching, we call it quenching because it involves like a quick reduction in temperature by using water. You know when you quench your thirst, you usually use water? Yeah. It's the same with quenching. Like you quench something by chucking it into water. Nowadays they use oil instead because oil doesn't boil as easily as water. So it's, I guess, more sustainable to use it. But anyway, looking at the answers here, this first answer here has nothing to do with heat treatment, so ignore that. And the last one has nothing to do with heat treatment either, although there are both ways of modifying metals. But these 2 here have to do with heat treatment. So if we think about the process of chucking your heated metal into water, that would be a very rapid cool down process. If we were to leave it in the air, that would be a much more gentle and slow cooling process. So the rapid cooling process is the correct one. So quenching involves rapid cooling. Now question 6 I think relates to chapter 3.1, looking at the properties of metals. Now, like, we didn't really go over this in too much detail. This question here is looking at the differences in properties of main group metals, versus the transition metals. And in fact, it goes a bit further than that, and it looks at some of the relatively inert ones, especially relatively inert metals. So inert meaning like they're not very reactive, they have very like mild properties. Okay. So if we're looking at relatively inert metals, right, ones that don't react too much, we can cross out a couple of them already. Or actually, we can cross out one for sure. Now, sodium is something that reacts with nearly everything, especially water. So if it so much as smells water or oxygen in the air, it's going to react. So it's not going to be likely to be found as a free element. So when we're talking about free element, it's like when we look in nature, we'll be able to see this element just by itself in its pure form, not as an oxide, not as a hydroxide, not as like anything that meant that it reacted with something else. So does not react here, hence inert. Now sodium is something that reacts really readily, so we can remove that. Now zinc, iron, and silver, these are all transition metals. Now just a note, the most inert of the transition metals are the ones that you find in the bottom right hand corner of of your transition block. So just give me. So when we look at the periodic table here, this transition block in the middle, this is where we're more likely to find inert metals, but it's in the bottom right-hand corner that we find the most inert of the metals. In fact, around here are the most inert of the transition metals. Silver and gold we know to be the most inert. Most likely to be found pure in nature. Zinc and iron are both first row transition metals, so they're much more reactive than silver. We can cross those out and we're left with silver. I think this is actually, unfortunately, one of those questions where you just got to know that like the most inert of metals are silver and gold. Which is why they're so good for jewelry, because like they retain their purity. They don't become oxidized easily, so they don't become like blackish or brownish with time. You can put water over them and they're not going to react. If you were to use iron in your rings and you don't alloy it, it'll become dark with time, so it's not so useful. Okay, question 7, another metals question, because it's talking about iron and zinc. Iron is often coated in zinc to form galvanized iron. So this is a modification of metals question. It's talking about the third way of modifying metals, the third way being coating it or plating or protecting a metal so that it can be better suited for its application. Okay, now here are a bunch of possible reasons for why we would coat iron with zinc. First one, zinc has a better appearance than iron. Don't think so. Zinc is less reactive than iron, so forms a protective coating on iron. This sounds reasonable. Let's check the other one. Zinc is more reactive than iron and will react instead of it. I don't think so. Now zinc is actually less reactive than iron, so this is not true. Zinc is less reactive than iron and will react instead of it. This is just a really like illogical answer. If it was less reactive, it shouldn't react instead of iron. So we can cross out these because they're not correct. And A just sounds wrong. So this is one of the questions where you can probably work out by deduction. But I think this is also another knowledge-y question. Like if you read through the textbook and you read that one of the case studies for coating metals is the coating of iron with zinc. I think the word that they used was that zinc is like a sacrificial metal, that you would rather have zinc react with air or with oxygen rather than iron, so as to prevent rust. Then this is why we apply zinc to iron. So just to add a note, reduces rusting. Okay, substance with a highest melting point here. This looks like an ionic compounds question, so we'll skip that. Question 9, another modifying metals question. So you can see that we're drawing from like all of these areas that we know, yeah? But modifying metals seems to come up a lot. Now, a metal could be made harder while remaining malleable. Harder while remaining malleable by carrying out the process of. Okay, and these are the heat treatments. And reduction is just a reaction that chemicals can do, and I don't think it has anything to do with making a metal harder or not, or more malleable or not. Now, quenching makes metals harder, but very brittle. You remember that with those hairpins that you heated and chucked into water, broken in first go. Annealing is when you like heat a metal to high temperatures and let it cool slowly. I do think that the metal remained reasonably malleable, like you could bend it back a few times. Wait, is that annealing? Slow cooling. I think both of these are actually possible answers, but tempering, I think, annealing does not actually make a metal harder. I'll add that. Does not make a metal harder. Makes it softer. Thank you, Joel. Yeah, it does not make it harder. It actually softens it so that you can work on it later. It's usually the first step in the heat treatment process so that we can we can do further work to the metal. So annealing is not the right one. Tempering is the right one. In fact, I was saying that you were annealing your pins when you were heating it and then moving it away from the flame. I think that's more like tempering, when you heat it and then cool it down slowly by letting it cool in air. Question 10, ionic compounds, we ignore that. Question 11, an interstitial alloy. So here we're looking at alloys now. Two types of alloys, substitution and interstitial. Interstitial means between atoms. Between, stitial. Oh, sorry, stitial means space. So between the atoms in this, between the spaces of atoms. Now, interstitial alloy, we're able to have like stuff in between the spaces of the atoms or the cations that make up a lattice because they're so small. And because you have these small atoms, you could say that in an interstitial alloy, we have atoms of unequal size. If you were to have atoms of equal size, you're more likely to have a substitutional alloy because those two different metal atoms would just like fit together in the lattice. Question 12 looks at the blast furnace, and I can see here that they're talking about something to do with the design of the blast furnace, why we can collect the iron more easily. So if I just quickly draw a model of a blast furnace. Now the blast furnace has two exit points at the bottom. So like once we put all the stuff in at the bottom, so at the top, all the stuff that goes in except for the air which we blast in through vents at the bottom. So air goes in here. The stuff goes in here. So your limestone, your coke, and your ore all goes in through the top. All the reactions happen in the blast furnace. And then at the bottom we get two like materials coming out. First we have slag, which is less dense and gets like siphoned off through the top vent, so the top exit point. And then we have the iron that is produced, the iron that is extracted from the ore coming out this way. Now the reason why the iron is at the bottom and actually comes out is because it's more dense. The slag is less dense, so it floats on top of the iron, and that is siphoned out the top. Okay, so we're going to look at the right answer that accounts for this. So iron produced in a blast furnace is easily collected as it is more dense than the reactants and the slag. That sounds reasonable. B, it is more dense than the reactants and less dense than the slag. Now that's not true because it is also more dense than the slag, so not that one. The rest of the products of the processes are gases. Now that's not true because slag is obviously a liquid in the blast furnace. And D, the iron is less dense than the products and rises to the top. Now that's not true looking at the design which has it coming off at the bottom. So it's B. Oh, sorry, A. That is more dense than the reactants and the slag. All right, question 13. A piece wire in a paper clip is bent back and forth until it snaps. This is what we call work hardening. So when you're applying, like, when you're working on a piece of metal and then twisting it back and forth or you're hammering it, that's work hardening. And what work hardening does is that it hardens the metal by making it more brittle, and it does that by reducing crystal size. So remember, the smaller your crystals, the harder the material, but the more brittle it is. How are we for time? We've got about 20 minutes. Okay, two more multi-choice questions. This is a ionic compounds question. We'll dodge that. Question 15, metals are usually solids at room temperature. So this is a properties question. This is a knowledge one. It's one of the things that you got to know or not. And I think it's actually not really like a big thing at all. It's just if you're very familiar with the elements. Now, pretty much all metals are solid, except for one. Some people are already calling it out. It's mercury. It's just one of the things that you would know, or not. So mercury is liquid at room temperature. Everything else is solid. All right, let's go on to the short answer questions. First question is ionic compounds. Let's ignore that. Second is ionic compounds. Let's ignore that. All right, question 2. We're looking at the reactivity series of metals. So reactivity series of metals is where we have metals and we can order them. Metals are ordered based on their reactivity. So in chapter 3, the only kinds of reactions that we look at between metals and other things are metals with water, metals with acid, and metals with oxygen. So how a metal reacts with water would be, so metals are usually react more vigorously with acid than with water. So if a metal reacts with water, you can expect it to react more with acid. If a metal doesn't react with water, then it might react with acid. Okay, and I think we found that the pattern of metals' reactivity with oxygen was a bit less easy to explain, like this series is different to water, but in any case, let's just have a look at what they've done here. In this question, they only look at what seems to be, don't delete my page, seems to be reaction with water and reactions with acid. In fact, reactions with increasingly concentrated acid. So you would expect there to be more vigorous reaction, vigor increases as you react metals with each of these. So let's have a look. Metal A, no reaction with water, gives some bubbles with dilute acid, lots of bubbles with concentrated acid. Metal B gives a lot of gas bubbles with water, and because the experimenter here saw that there was a lot of gas bubbles with water, he didn't bother reacting it with acid. And I think that's a good idea, because if it was so reactive with water, why would you risk reacting it with acid, maybe making an explosion or something? So very reactive, it looks like B. So I'll mark this as very reactive. I like to do this, like when I'm reading tables, I just add notes to things. Metal C shows no reaction with water, dilute acid, or concentrated acid. So it looks really unreactive. So I'm going to go very unreactive. Metal D gives no reaction with water, but then gives lots of gas bubbles with dilute acid. Interesting. And then violent bubbling of gas with concentrated acid. All right. So we're able to establish B and C as very reactive and very unreactive respectively. And I think the main thing is being able to figure out which one is more reactive between these two. And looking at the description of which one, looking at description of how each of these, so A and D, reacted with dilute acid, you can probably see the difference. So D looks more reactive than A, just by the virtue of having produced more gas bubbles than A. D, more reactive than A. Okay, and then we just need to order them in the first question. Write down the reactivity of 4 metals from most to least reactive. So the most reactive we established to be B, very reactive. B is more reactive than the next one, which is D. D is more reactive than A, and A is more reactive than C. Okay, now give an example of a metal that A to D that might correspond to calcium and lead. All right. So let's have a look. Now, to answer this question's a little bit tricky because it needs for you to know about what are possible inert metals. You need to know about inert metals, such as silver and gold. And you need to know about reactivity trends. Okay? Now, just in general, reactivity trends, as you go down a group, you have more metallic character. Therefore, metals are more reactive. You also need to know that towards the left of periodic table, you have more metallic character or more reactive metals again. So the group 1 and group 2 metals are the most reactive. Group 1 and 2 are considered the most reactive, with group 1 being the most reactive, period. Okay. All right, let's have a look. What I would do to answer this question is to tentatively, with what I know, mark down what each of these metals that we've been given, what they might have been, okay? Now C showed no reaction with anything, which means that it's inert, like it doesn't want to react with stuff. Now we know that the inert metals are silver and gold. Well, two examples of inert metals are silver and gold. So I would go with, for C, I can already give what it might be. It could be Ag or Au, silver and gold. Metal B was super reactive, so I'm going to guess that it's one of the elements on the left-hand side of the periodic table, probably in group 1. If you've ever seen potassium or sodium react with water, pretty violent, like you wouldn't want to try those with acid. So I'm going to say this is possibly a group 1 element here, maybe potassium. All right. Now metals A and D, this is where it might be a little bit tricky. And I think A and D, because they both react with acid, but one reacts more with acid, I think this is where we need to just apply our knowledge of the reactivity trends. That as you go towards the left of a periodic table, you see more metallic character. So D is more reactive than A. Calcium is more to the left of the periodic table than lead. Sure, lead is like further down a group, but lead is also in, if I look at the periodic table, let's just so I can show you. Lead's actually in group 14. And group 14, if some of you know, or you can see actually, at the top is carbon. Carbon's a non-metal. Carbon likes to form covalent bonds and stuff. So what we see is that group 14 is one of those weird groups where we see non-metals at the top, metalloids in the middle, and then metals at the bottom. And so, like at the bottom, you barely get a metal, is the idea. Like it's a metal that's only just a metal. So you wouldn't consider it too metallic compared to, let's say, one of these elements here in group 2. So looking back at the question, they're asking us to work out which one is calcium, which one is lead. I would say calcium is more reactive than lead, just because it's further to the left of the periodic table, and it's in a in a group that is full of metals. So the more reactive one was D. So I'm going to say calcium is D and lead is A. And I say lead is A and not C because C is an inert metal and lead's probably not inert, most likely not inert. So we'll go with that. All right, question 3 lists a bunch of metals and suggests a use for the metal, giving a property for that metal as well. So copper, a possible use, you've probably seen copper wire. The reason why we use copper as a wire is because it's ductile. We can draw it out easily into a wire. Silver, what we use it for is jewelry. And the property that relates to that is it's lustrous, so it's shiny. So it has the, what did I call it? Bling. Jewelry and silver and gold, they're both like blingy metals. Very shiny. Iron. Iron is used in tools, and the reason why we use iron in tools is because it's pretty hard, yeah? And aluminium, they use it for, let's say, foil. We use it for aluminium. We use aluminium as in this way a lot, as aluminium foil, because it's malleable, so you can roll it out into. Oh, sorry, it's also ductile. Because it's ductile, you can roll it out into thin sheets. I might give both of these. Do you know how aluminium foil is very thin and very like flat, and you can like flex it around and it won't break so easily? That's because It's ductile and malleable. Now, these aren't the only answers. You can come up with other possible uses and other properties that relate to those uses. It's one of those questions that if you give a reasonable answer, you'll get a mark. All right, periodic table. Let me just look quickly whether there's some ionic stuff in here. No. But this does look at metals versus non-metals. So I think it's relevant enough. Symbols A to F of any metals. Okay, so let's have a look. Group 1, Group 2, transition block. So I'm just going to label in this scarcely labeled periodic table. Group 13, 14, 15, 16, 17, 18. Or group 3, 4, etc. Whichever one. Now the metals we find in groups 1 through to 13. And you get, I guess you get blocks of metals down here. I'm just going to shade roughly where the metals are actually. So the metals are down here. I'm going to shade all of this, just easier. These are where all the metals are. Oh, and down here too. So symbols of any metals. Now E over here, that's in a metal area. B is not quite a metal, because the top of group 13 is boron, and boron is actually not a metal. C over here, that's well in the non-metal territory. F, D, A are all non-metals. So the only metal that on that periodic table is E. Okay. Interestingly though, this next question here, this is a non-metal. Let's ignore that because it's an ionic, refers to ionic compounds. Actually, let's ignore this question here because it's ionic compounds, and C is ionic compounds as well. Let's ignore both of those. Okay. Sorry, remember this sac here has combination of both metals and ionic compounds, so we've just got to ignore some of the stuff. Question 5 looks at modifying metals again, so chapter 3.5. All right, so they're asking for reasons why, and these are both relating to alloys, why alloys have different properties to those pure metals. Question 5a says that alloys are usually harder than pure metals, and we have to explain this. Alloys are usually harder than pure metals, and it's 2 marks, so they want 2 reasons. All right, so with a question like this, I'm okay with dot points. I'll put out 1 dot point, ready for my first point, first reason. Now, why would alloys usually be harder than pure metals? So I think about the 2 possible types of alloys. The first one being interstitial, and then the second being substitution. Now, with interstitial alloys, again, I'll draw an example of, just a generic example of an interstitial alloy. The pure metal looks like this, with the cations, I guess, in this metal lattice being arranged like so. Now, if the metal was to be hard, right, the harder the metal, the less likely it is that you can move these metal ions. With an interstitial alloy, you start to introduce stuff in between them, and that affects how easily they would move over each other. In fact, it makes it harder to move the layers of atoms past each other. And because it's harder to move stuff, right, harder to make them change their shape, that would mean that this alloy here is harder due to less movement. Harder due to less movement between layers of atoms or cations. So the first reason, and I would be specific and I would say interstitial alloys, if I could spell, interstitial alloys are harder because the inserted atoms prevent movement of the of the layers of atoms, layers of metal atoms. Let's go with that. Okay, now that I used up both lines with that, I reckon they should give us more space than just this. So I need a second point. Alloys are usually harder than pure metals. Now I'm going to be honest, I can't actually think of a second reason. And so because of that, I don't know if I should be here teaching you guys, but you do have a solution book, and I do wonder if they give another reason. So have a look at that. All right. Question B. Alloys usually have a lower melting point. Usually have a lower melting point than pure metals. All right. Usually have a lower melting point than pure metals. Now where we would get a measure of the melting point from, melting point relates to the strength between the metal atoms. Sorry, I'm going to write here, strength of the metallic bond. And just going over quickly this idea of the metallic bond. Just going over quickly here the idea of the metallic bond, okay? The metallic bond is the strength of the bond between the metal cations and the sea of electrons. So remember, in this metallic bonding model, what we have are cations that are attracted to this sea of electrons that is formed by them having donated those electrons into the space in between, right? Now this metallic bond can be affected, so it could be interfered with by a couple of things. And I would say, I would use substitution alloys in this question because I think you can explain it this way. So with substitutional alloys, for example, when you have a different size atom, that does a couple of things. First, it disrupts the structure a little bit of this lattice, which makes it easier for you to be able to separate the atoms. So that would lead to a weaker metallic bond and all of that. I know we're running against the clock a little bit here. But I think the rest of the question, what you have to refer to, I would invoke the substitutional alloys and then show how their metallic bonds might be weaker. Okay? All right, now we had a couple of other questions. This here was ionic compound, so we were going to ignore that. Here, they would ask you to draw the structure of magnesium. They're asking for you to draw the metallic bonding model for magnesium. So as long as you know how to draw the model, which is just what I did up here, but it needs to be labeled here. So you need to label this with magnesium 2+. And here you have free electrons or delocalized electrons. Then you would have answered this question here. Now this is a 2-mark question. So if you draw the lattice, you label it, that would be 2 marks. All right. Now I know that was really quick, but this is recorded, so you can review it at your own leisure once I upload it. All right, thanks guys for listening.